Good morning, everyone. I hope everybody's enjoying their snacks and drinks. My name is Pablo Arevalo with my partner
Sheehan.
We're from PCH Industries, and we're here to present our processor, Protocore. We came up with the name due to the fact that this is our company's first processor, and the prefix proto means earliest form, so we decided to go with Protocore.
So we just had our introduction, so this is our agenda for the rest of the time. We have our ISA design, we have our block modules, and then we have enhancements, and then more Q&As. So for our memory structure, we have a Harvard architecture. It's a 32-bit address space, and it has 64-bit memory operands stored in Little Endian format. So you take the lower, and you store it first, and then the upper bits, they come in afterwards. So for the register set, we have data types are 64-bit integer and floating point. Our registers are all 32-bit registers except for the integer and then the floating point. So as you can see, 32 integer registers, and they are 64 bits. We have the 32 floating point registers, which are 64 bits. And then we have our instruction pointer denoted by like IP, stack pointer, SP, memory address register, MAR, and instruction register IR. And then we have our read buffers, write buffers, and our FP buffers. So for the addressing modes, we have immediate, register, and register indirect. So for the immediate, we have like 8-bit, 24-bit, 32-bit half words. And then the register indirect contains like load, store, jump, and calls. So for we have single, double, and triple operands. We have the conditional jumps, unconditional jumps, calls, and returns. We have flag processor instructions, immediate operands, and floating point instructions. So for the triple operand, you can see it has source 1, source 2, and the destination register. Double operand is just without the source 2 register. Single operand, the destination is whichever source 1 register is. And then we have a conditional instruction right here. For the jump and call instructions, it's almost the same thing. We have the flag processor instructions and the immediate operands, and we have our 8-bit immediate value. So for the block modules, this is our top module. So basically, we have our CPU, and within is our CU and our EU. And then so we also have these memory, which is we have two memories: the data memory and the instruction memory. And we also have the input-output module. So that whenever the input-output module interrupts, the CPU will respond with the interrupt acknowledge. So this is going more into detail. So we have our CU and our CPU. So our CU contains our finite state machine, and then these are all the control words sending it to the execution unit. So here I will hand it to Pablo.
Okay, and here we have our execution unit, more in detail. It's still kind of generalized, which I will go a bit more into detail for each module. In the upper right, left box, we have our floating point integer data, our data path, and our right box we have our integer data path, and then our VIU here at the bottom, which I'll be going into detail. So for our integer data path, we did make one modification for the baseline, and it was basically just having a third input on our SMUX, so that way we could bring in the data from our data memory directly into our ALU, as opposed to writing it first to the reg file, which would add an extra cycle. And this is in our VIU. We added a couple of markers in front of our MAR and SP registers in order to implement all of our instructions. So as you can see, for the MAR, we have an increment and also the ability to set it to 32-bit 0. And for our stack pointer, we initialize it at 3FE, and we also have the options of increment and decrementing it. And our SMUX decides which address to load into the data memory.
Did you have to have 3FF come into the MAR select? Like for interrupt handling?
No, we did that in our IP register.
No, you were just going to read that location and put that into the IP. So we'd have to read 3FF, and then, did you guys get that far?
Yes, we did.
For handling interrupts, in other words, an interrupt happened, you'd go out to 3FF, read it, and then put whatever address was in there into the IP. But you'd have to read that location.
I might not put it in there. I'd have to go back and read
Okay.
my notes. Yeah. Okay, and this is also the right above 0 IP and IR registers, which we also added mux, so that we can avoid adding extra cycles. So for our right above 0, well, we bring in the IP or the IR directly, and for the IP, we could bring in the right above 0 or the read above 0, and as well as adding the IP and IR for immediate instructions.
What did you need that 32-bit 0 coming into right buff 0 for? So there's 32-bit 0. What was that used for?
For the right above 0?
Yeah, what instruction needed that?
Oh, those are just to initialize it at 0.
Oh, okay.
Yeah.
But the high side you didn't initialize to 0?
Yes, we did. We just didn't state it here in our slide. So these are for our read buffs. We also use notice in front to provide extra options. We could directly load the I data coming from instruction memory, or initialize it as well with 32-bit zeros. And now we'll move on to our enhancements. These are just basic instructions that we decided to add to our baseline, which contains 80 instructions. We thought it was necessary to add these instructions just as an option to the engineer, whether or not you want to use it or not. Below each instruction is the Verilog code for it, with the truth table below it. We also implemented a parity flag. Parity flag basically checks for the even bits set to 1. So when there's an even amount of 1s, then it's set to 1. And this was our Verilog code that we used to implement that. So what we do is we take the product Y and we go through all the bits. We do a for loop, and then we either set the flag to 0 or 1. Using the parity flag, we also implemented these instructions, which is the jump if parity and jump if not parity. And due to our time constraints and multiple errors in designing our baseline, we weren't actually able to implement our vector data path or barrel shifter or UART, but we are working on it currently. So yeah, that's about it. Are there any questions?
So you did parity the best way you know how to do at the time.
Correct. We wanted to use that for our UART
Yeah.
in order to make
But
sure that there's
what's the best hardware implementation? Since we're hardware designers, we probably wouldn't do a for loop. That's what programmers do. How would we implement it without using a for loop? In other words, the parity exclusive word with the YI. That was your.
Yes.
Was that talked about on Monday, Sheehan? Weren't you here?
Yeah, I was here. But
Somebody did parity, right? One of the groups. We talked about how we should do, as hardware engineers, how should we implement parity? We're not software people. You know, we do stuff that happens ASAP. How do we do it?
Just a massive 64-bit XOR.
Yeah, it's just XOR. So it's fast gate level XOR. Some type of hardware implementation, so it's just fast. But it's good, you know, the thought about it's good to have it. x86 has had it since its inception. They had a parity flag for all instructions. And they had the jump parity, jump not parity. So it's proves it's useful to have in your processor. So that was good. Anything else? Okay, you guys, thank you.